Hello, here we will look at the process of diagonalization. Before just talking about what it is and how to find such a thing, I will start with the motivation. Let's imagine an operator, say on the coordinate vector space of dimension 3. And the question is, can we find such with the given spectrum? Say spectrum consisting of 3 different numbers, 1, 2, and 3. And the answer to this question is yes. There is always an operator with these eigenvalues, at least one. The easiest example will be just to make coordinate vectors, eigenvectors for these eigenvalues. So to say that the operator moves the first coordinate vector to itself, making it the eigenvector, an eigenvector with eigenvalue 1. The second will be scaled with coefficient 2, and the third with coefficient 3. And writing these in a matrix form, so writing the matrix for such operator, we'll have matrix of diagonal entries 1, 2, and 3. All of diagonal entries will be 0. Such matrices are called diagonal, and these are the easy matrices for computations. And that is the reason for diagonalization. So we are to start with an arbitrary matrix. Starting with an arbitrary matrix, we can sometimes, most of the time, we can find a better shape in a different way of looking at the matrix, a better shape of it, which will be diagonal. And this process is called diagonalization. But continuing with motivation, I will look at other examples of a linear operator on a 3-dimensional coordinate space, which will have the same spectrum. So I could start with my diagonal template and then scramble it, perturb it with, say, any invertible matrix. Let me just take an invertible matrix, say this, 1, 0, 1, 0, 1, 0, 1, 0, 2. And then the inverse to this matrix, please check me, I will not be doing a computation here. It will be 2, 0, negative 1, 0, 1, 0, negative 1, 0, 1. So please check that these two matrices are inverse to each other, but what I will do, I will take my matrix M and sandwich it in between G and G inverse. So that will be new matrix, I will call N. This process of multiplying by G from one side and G inverse from the other doesn't change the determinant. And as a result, it will not change eigenvalues of M. So there will be the same eigenvalues for M as for N. And that is a guarantee that I'm going to have the same spectrum for the matrix M and for the matrix N. So there will be still the 3 numbers we start with, 1, 2, 3. Let's see what the matrix N is. So let's just do the matrix computation, multiplying G with our diagonal, and then concluding with G inverse. Let's multiply the first two first, and then we'll have 1 as the first entry, 2, and negative 3 as, sorry, negative, I shouldn't have negative 1, so I'm making a mistake here. It should be positive 3 because, yeah, that's what G is. And the continuing with the product, will have these by that will be 0, this by that will be 2, this by that will be 0 again. Yeah, that should be 0 as well. And continuing, so this entry will be 1 times 1 will be 1, so that is positive 3 again, to stress it. That row by the column will give 0, and that row by the column gives 6. And the last matrix, the G inverse, is still this. So finishing the computation, let's multiply the two matrices here, and we'll have this by that will be 2 without 3, it will be -1. This by that will be still 0. This by that will be -1, and 3 will be +2. That by this is 0. Here we'll have 2, 0 again. Pattern of zeros persists. So this line by that column will be 2 without 6 will be -4, 0, and then -1 and 6, +5. So that is what matrix N is. And again, the claim is that this matrix has this spectrum, has these eigenvalues 1 to 3. So imagine that we're just given this matrix, and can we see the way it came about as the perturbation of the diagonal of an easy diagonal matrix conjugation with this G and its inverse? So let's forget that we know so much about matrix N and start honest and compute its spectrum. By computing the characteristic polynomial, finding the roots, and then solving homogeneous equations, one for each root. The characteristic polynomial will be the determinant of the matrix N without with t subtracted from its diagonal entry. So it will be -1, -t, 0, 2, 0, 2 without t, and then 0. -4, 0, 5 without t. Again, if we can use row or column expansion, we should. It gives us factorizations. It makes possible factorizations more apparent. And the easiest row or column to expand along is just the second. So row 2 expansion will be giving us 2 minus t as first factor, and then the determinant of this 2 by 2 matrix, and that will be -1 -t times 5 minus t, and off diagonal product will be with negative sign will be 2 times -4, so it will be just +8. We need to compute this quadratic, and then t squared is the leading term. The free coefficient is -t and -1, so +1, and then -5. So there will be -4 total. And the free coefficient is -5 and +8, totally into 3. Again, this is a nice quadratic, which we can factorize, giving us the roots we started with. So there will be t minus 1, t minus 3. And the result, the spectrum is the same. So we verified that indeed conjugation doesn't change the spectrum, but of course it doesn't change because the determinant of a conjugate is the same as the determinant of the middle term. The determinant of G and the determinant of its inverse cancel out, whatever they are. They happen to be -1 in this case, but it doesn't matter what they are at all. They just cancel out, and the determinant of the middle term will still be the same as the determinant of this. With t subtracted from diagonal, it still be the same. So characteristic polynomials are identical for M and for its conjugate. Now let's forget, keep not remembering what we know about matrix N, and compute the eigenvectors for the eigenvalues we have. So starting with the first in the natural order with the eigenvalue 1. We take matrix n and subtract 1 from the diagonal entries. That will be -2, making -2, 1, and 4 on the diagonal, then these zeros, and then the off-diagonal non-zero entries as they were. And yes, the first and the last rows are proportional, and we can eliminate them. So doing it all together with scaling of the first row, I will have 1, 0, -1, 0, 1, 0 left in my already reduced row echelon form, a solution which I can make by making the free variable the third coordinate to be 1. There will be first coordinate will be also 1, the second coordinate will be 0. So that is the eigen vector for eigenvalue 1, whatever it is. Let's continue with the eigenvalue 2. Now we are subtracting 2 from the diagonal of n, and we will have -3, 0, 2, all zeros, because these 2 will be eliminated, and -4, 0, 5 without 2 will make it 3. Again, the matrix is singular, the matrix is degenerate, giving it at the end of the Gauss elimination an eigenvector, a non-zero one. And what we can do, we can perhaps subtract the last row from the first, creating the pivot 1 there. Then we will have -1 here, and we'll have the line of zeros, and we'll have -4, 0, 3. Then I could do elimination in this first column, row 3 plus 4 copies of row 1, and we will have a 0 and 0, and 3 without 4 will be -1. So all in all, we will have 2 pivots, and we will have a 0 line. 2 pivots being in the first and in the last coordinate. These 2 pivots will make these coordinates 0, and the generic solution for this for the corresponding homogeneous system will be proportional to this one. So this time the free variable is the second one, and the 2 pivots are to be made 0. We are left with 1 eigenvalue to compute the eigenvector for, but already look at what's happening. So the first vector is nothing but the first column of our matrix G, used to scramble the diagonal M. The second is the second column, so I imagine you're guessing what the last eigenvector is going to be. Again, we take matrix N and subtract this eigenvalue from the diagonal entries. That's what the result will look like. So 5 without 3 will be 2. Again, the matrix is manifestly singular. The first and the last rows are identical. So eliminating the last, scaling the second, and maybe scaling the first. We will have this system to solve. Again, the second equation says that the second coordinate of the solution has to be 0 no matter what. And the first equation is saying that the free variable we have in this row echelon form, the free variable, if we make it 1, the first coordinate will be half that. So it's better to make it 2, so that we'll end up with the smallest possible first coordinate, and that way we will see our last column. We could have scaled this by any coefficient, so with the first vector and so with the second. That is the freedom. We could choose any vector proportional to these three as our choices for eigenvalues, but the result will still be the same. So we recovered effectively the matrix G, which we used to modify our diagonal matrix into something looking more menacing. And that is a general method of diagonalizing if it is possible. So we can diagonalize a matrix if we have enough eigenvectors to form a basis in our vector space. If we have three eigenvalues, we will have one eigenvector for each, and by just general principles, these eigenvectors will have to be linearly independent. So that is the easiest situation where the spectrum is all different numbers as many as the dimension of the vector space we are operating on. And then for each number, for each eigenvalue, we have an eigenvector, and we have enough to build a basis. And using them as new bases, we can manufacture this conjugating matrix that will be the matrix of changing bases. So that equation which we used to manufacture our n in the first place is a result of the computation. Now we take new basic vectors, we build a matrix out of our eigenvectors, and then this matrix will conjugate our given matrix to its diagonal form. And the diagonal form will have eigenvalues on the diagonal in the same order as we used for building the conjugated matrix. And then we'll have to finish the conjugation by putting G inverse on the other side of the diagonal matrix. So that is called diagonalization. And that's what generically is possible. Again, the condition is that we have enough eigenvectors to form a basis. It could be that our eigenvalues repeat, that we have multiple roots of a characteristic polynomial in a characteristic polynomial, but that's not necessarily a bad thing. We still have a chance of having enough eigenvectors. Let me finish with an example where diagonalization is not possible. That will be a matrix of size 2, the smallest possible, all ones but this 0 of the diagonal. If we compute the characteristic polynomial, we will have 1 minus t squared, which will make the spectrum of this matrix to consist of just one eigenvalue 1. And then continuing with the story of finding eigenvectors for this eigenvalue, we will only have one solution, because when we subtract 1 from the diagonal, we will have this result, which will be saying that the first coordinate, whatever it is 0. So any eigenvector is proportional to the second coordinate vector. And we only have one up to proportionality. It's not enough to build a basis in the two-dimensional vector space. So this matrix N is non-diagonalizable. But that is a rather special case, is it an exclusion to a more or less general rule that randomly chosen matrix will be possible to write in this form as a diagonal matrix sandwiched between an invertible and its inverse. In the process of finding diagonal matrix is just process of finding the spectrum, finding eigenvalues and putting them in some order on the diagonal, and then eigenvalues are ordered. Eigenvectors for each of the eigenvalue will be used as the first, second, and last column of the transition matrix G, and G inverse is whatever it is determined by G. So that is the process. We will have more examples in a different video.